Welcome. So, dear guests and speakers, we are very excited to welcome you to the by now seventh NFDIxCS Soiree. And this series is made with the intention to offer an interactive platform to discuss relevant pressing topics in and around research data management from within our consortium and beyond. And today we want to speak about the topic of proofs, traces, and reproducibility, advancing research data management. And I want to briefly introduce our two presenters today. We have Fabian Huch from the Technical University of Munich. He will present how interactive theorem proving connects mathematics and programming and how we can use this to enable scalable and reusable tools. And Reza Salkhordeh from the Johannes Gutenberg-University in Mainz will explain how HPC-IO traces are transformed or can be transformed into reproducible execution environments. And we can use the abbreviation, if you agree, called REEs. For high-tech computing. And after the talk, we all have the opportunity to engage, ask questions, and participate in the discussion. And please note that this event is recorded, and participation is only possible if you consent to this. So if you don't consent to this, you can also feel free, of course, to leave this call. And I wish us all a very inspiring and informative evening, and I would welcome our first speaker, Fabian Huch. Yeah, thank you.
Yeah, thank you so much for the nice invitation and organization, everything, and introduction, of course. Yeah, so I want to talk about interactive theorem proving, and I think I have to briefly introduce the topic first because I'm sure that most people won't be familiar with it. And so let's try that in 5 minutes. And for that, I want to start with something that probably every computer scientist already knows, which is SAT solving. So in SAT solving, as you probably know, we have formulae, and those are propositional formulas. So we have 3 variables, those are A, B, C here, and they can be assigned to true and false. And then we have connectives between them. So yeah, the conjunction, disjunction, negation, and so on. And we can simply represent them with truth tables. And then the questions that we're interested in SAT solving is typically something like whether a formula is always true. So if it's a tautology, no matter the assignment. And the way you would verify this with a SAT solver is you simply negate the formula, and then you call the actual SAT solver, which will check if all possible assignments for the 3 variables result in result in false, essentially. So if the formula is actually unsatisfiable, and that gives you a decision procedure for this fragment. Now, the actual research in this field is, of course, how to do this as fast as possible in practice. And in contrast, in interactive theorem provers, we want to also prove that formulas hold, but we don't want to be limited to just Booleans, right? So we want to express basically everything that is expressible in mathematics. We need things like functions, quantifiers, and so on. And so here you can see the Cantor's theorem. So that basically states that there isn't a surjective function from a set to its power set, although this is in higher order logic. So this is in the Isabelle interactive theorem prover system. This is what the ITP stands for. I don't expect you to read all of that. Most computer scientists will at some point in their career probably have seen Cantor's theorem, but maybe not remember it. But that's not the point here. The point is to get a feeling of how things look in interactive theorem provers. Well, the downside is if you are as expressive as this, then a proof of that is no longer a push button thing. You actually have to write down some proof structure. So this is what you would write in Isabelle. So you can see that you do things there, like you assume that there is a function, then you obtain that instance, and so on. Don't look at the details. The important part is that here you actually have to do all of the proofs from start to finish. And in this, and here this is just the rough outline. You still have to fill in the actual gaps to have no holes whatsoever. And we do this with a bundle of proof search methods that are incomplete, but that I input and the system tells me if it's okay. And then this is how it actually looks like when inside the interactive theorem prover. So you can see there's a sort of IDE, and the whole thing is very interactive. We have this mathematics loaded in here. You can see in this demonstration, there's the cursor at this position, and there's some state to be explored. So we have theorems, local assumptions that hold here. We have the goals that we need to prove, and so on. And the important point about that is that in interactive theorem proving, to interact with your data, you really need the theorem prover because your data in the end is the formal documents that you're working with. And that's different to most fields where you would probably collect the data in some way that you can then post hoc analyze it in an offline way, say as CSV files or something. But this also means that you have to be able to run the interactive theorem prover again exactly the same way. So reproducibility is really, really important for interactive theorem provers. But at the same time, interactive theorem provers are extremely complicated pieces of software because they have to do so much and so difficult mathematics. And so this is a difficult problem. And there have been advances recently in mainstream computer science to address this problem. So there are tools like GUIX or NIX today, which can create builds of software that are reproducible even to the byte level, which I find very promising. And I think that as a society, we profit if we can all make our experiments more easily reusable. Yeah, but this is difficult in a system like Isabelle, which has evolved over so long. We have our own operating system abstractions and so on. And then these reproducibility tools we have, they are built for compiling C and C++. So they're not really, they don't fit too well, but if the only tool that you have is a hammer, then we just have to pretend to be a nail. And so it can be very difficult to fit into these tools. And this is what I'm writing in my blog post about. So make sure to check that one out. Okay, I think that's it from my side. So I don't want to take up too much time. So please, Reza.
Thank you. Thank you, Fabian. Yeah, we will for sure at the end of the two presentations, I will also share your blog post so everybody interested can also dive in directly or whenever you guys have time. And without further ado, I would like to give the microphone hand it over to Reza. And after that, we can have our questions. Hi, Reza.
Hi everyone. So let's see if I can share my screen. Okay, it should work, right?
Yeah, looks good.
Okay, perfect. So hi everyone, and thanks for the invitation. What I want to briefly discuss right now is that we try to create an initiative to collect the traces of IOs in HPC systems. And one of the very important parts of that was related to the things that we are doing in NFDI for computer science. Why we do profiling or why we do tracing in the context of HPC systems, although it can be generalized to other domains also, is because we want to understand how applications are behaving and how storage systems that are storing our data are behaving for different applications, different types of metadata operations like opening, deleting, renaming files, the different I/O patterns that applications might have, and also these I/O requirements that applications have. What kind of impact they might have when we are using faster storages or slower storage systems. But the challenges in collecting those and comparing those is that, of course, applications are not running on the same environment. We are not capturing everything with the same tools. And there are many hardware dependencies, software dependencies in the clusters, and all of these makes it a lot harder to compare and collect standard traces. What we are trying to do here, and why this initiative is closely related to NFDI for computer science, is that here in NFDI for computer science, we are also trying to build the profiling tools, tracing tools, standardize their outputs. And in addition, what we do is that we create an analysis tool that allow users to simply upload their traces, compare them with the others, with different applications, or simply finding what they want to do in the domain of, let's say, storage. So we try to collect as much context as possible from these traces, the applications, version of the libraries, version of the applications, number of nodes, hardware that these traces have been captured on. We want to provide a tool that people from different disciplines, that people from physics can check what kind of applications have the same I/O behavior as some applications in the chemistry domain or computer science domain. One of the emerging use cases right now that's very hot in the past 1 or 2 years is AI and machine learning applications. And since they are developing very fast, everyone wants to know how good their approach is working on storage, how they can make it faster, how they can make it more efficient. So using these tools can make it a lot easier to just upload your traces and then get an analysis on top of those. So, of course, application developers will benefit because they can just get some insights on their applications, on the I/O behavior of their applications. They can even compare their I/O behavior to the other applications. And for storage developers, for people that are trying to optimize storage, all these traces will make it a lot easier to understand what applications need. So what we should optimize in a HPC system. It can be also generalized in a normal data center, in a cloud provider, what kind of IOs are more pronounced and what should be more optimized, or what are the bottlenecks that they should basically work on that. So basically we have a submission interface. Users can upload their traces. We obfuscate, we anonymize, we verify the traces, and everything to make these traces standard can be done in this step. This can be extended to anything that is basically needed or comes later. We create various plots, different types of plots, 2D plots, time-based plots that helps users to actually see the behavior of their applications. We also provide comparison tools to compare two traces from the same application or different applications, same application on different hardware, and anything like that can be basically compared. And we also provide a way to access the data along these comparison tools, along with these analysis tools on a system that can be accessed 5-10 years in the future. These are just one or two samples of different applications. You can clearly see that these applications have different behavior, although I've tried to put some applications that are easier to see the difference between them. You can see that this application has 2 bursts and this one has a 1 burst that is lower compared to the other one. Here you can just compare running with different sizes, with different number of nodes, let's say, and then you can compare the spikes that you have on where a lot of I/O is happening. You can compare the values of these. You can compare when they are happening, or here you can compare that between these two clusters. You can see that, for instance, when the peak happens in the percentage of the runtime is different. So it depends on the hardware capabilities of these basically clusters. So we try to work with the FAIR principles and provide them. And what is interesting for us here is the reusability, basically. And reusability basically means that we want to allow users to also run these tools, run everything that we are providing, the source code and also the traces that we have been gathered, get the analysis, and also upload their own traces and get their own insight about their own data. This was actually one of the very first few feedbacks that we got from people that we have introduced this initiative. And the question was that how we can run it locally on our company or in our institute and get the insights about the traces of the applications that might not be accessed publicly. So this reusability, this part that is interesting for us here, will allow everyone to use the codes, the traces, and also providing their own traces. So basically, if I want to conclude here, we want to adhere to the scientific data management, any best practice that is accepted, we want to try to adhere to them. We are right now have integration with Zenodo to store our data for a long-term access. This can be also extended with anything else that, let's say in NFDI for computer science, we also want to take. We also provide those for anyone that wants to reference to these data set that they have uploaded to this analysis and then use it in papers, in white papers, or in their talks, let's say. And of course, we want to have as much transparency as we can, and also we want to have reproducibility in the research in the area of HPC-IO, which is why having a container version, having an RDMC, or having an REEs for our website and for our analysis tools is very, very important for us, and makes that will actually make everything that we have promised to publish. It will allow us to basically publish and keep our promises. So that was a very quick introduction, and I'm happy to answer any questions.
Yeah, thank you, dear Fabian and Reza, for this really brief, concise intro. I have prepared some questions for you in the audience, but I've seen that there's by now more participants, so I wanted to give you the possibility to ask some questions. If not, I will be happy because I have some as a non-expert. It's also interesting to have all this material and to digest it. But yeah, I just want to give you Martin, I mean, you are an expert, and Christian Riedel, the opportunity to pose some questions to our speakers. And I mean, maybe you will still be thinking about some. So I would be interested, Fabian, as I already said, like I'm not an expert, so for me, like many of the contents that you are like presenting here starts to get a bit more familiar to me, but it's still quite new. So in simple words, what do you what would you say has the theorem proving that you just presented has to do with advancing the goals of the NFDIxCS initiative to improve research data management infrastructure?
So I think I see the field of theorem proving mostly as a kind of a consumer of NFDE technology. So it's very, I think it's really necessary that we start to invest a lot of energy into the direction of making research more reproducible. The current status is that whenever you want to reproduce the research that someone else did, you have to invest an unreasonable amount of energy and time to do that. As I said, in theorem proving, it's especially bad if there's a proof that a formal proof that you have, but you can't replay it, you can't re-execute it, right? That proof is basically worthless. It doesn't help you a lot, other than the abstract knowledge of, oh, the statement must be true, but true then usually only means true with respect to these and these axioms and those definitions. And so it's really crucial to be able to just pick a piece of research that someone did and then immediately replay the same proofs on your system so you can explore the structures. Yeah. Sorry, you muted?
Yeah. 1 second. I saw. So I was really fascinated also in editing and working together with you on your blog post that I just shared for everyone. Is that I've also been reading about theorem proving, and it has been described as both art and as science. So can you maybe share a practical example how it is used and why has this been described as an art and a science? And at the same time, that sounds interesting.
Yeah, absolutely. I mean, in the end, it's mathematics, right? Or that's what it boils down to. But then you also have the computational aspect, and just that intertwined, I think, is why people would describe it as such. And then, for example, so the things that people formalize, well, broadly all kinds of mathematics. I think computer science related mathematics are obviously overrepresented because there's so many computer scientists working on interactive theorem proving. But it's really it's a mixed bag. So we have um, many different fields with lots of formalized material. There's also applications from industry. So for instance, we have colleagues at Apple or AWS who actually use Isabelle to formalize some of their, say, security protocols, some of their implementations, their software that to just make sure that it works. So verifying certain properties of software is also a very important field for interactive theorem proving, especially because it's just so easy to get software wrong, and it's actually more difficult to get abstract mathematics wrong. I think that happens far less frequently.
Yeah, thank you for sharing that, Fabian. I would now like to go to Reza's input. And yeah, I don't see any questions right now so far, so I will just like continue with some of the questions that I found interesting. So I know this is like for really like for starters, but I know that there's also people interested in your topics that really come from a non-expert side. So could you briefly say again what are actually HPC-IO traces? Why are they so important in high performance computing? And how can we make your analytical tool that you've described more reproducible? And maybe as a last question, is there a difference between reusability and reproducibility? Because like you guys have used these words a lot, and yeah, maybe we can differentiate between those two. That would be interesting.
Yeah, so thanks for the questions. Basically, why these traces or gathering them or analyzing them is important for different disciplines is that many people that are working in physics domain, in aerospace, in chemistry, or any other field that are doing a lot of computations, they have uh, expertise in their domain. They write their code, applications, and do their computations, but they don't know of the complexities that we have when we are accessing the data or storing the data. So this is really the users of these storage systems are not familiar with what we are doing, and sorry, and we are also not familiar with what they are doing. So having these traces will bridge the gap. It will allow us to know how these different applications are behaving, and also it will also show them that what kind of what part of their applications is causing the bottleneck for them, and which part is basically should be optimized. So this is basically a tool to bridge the gap between these two or different disciplines.
Yeah, thank you. And also with regard to your beautiful guide that we just posted recently on how to make HPC data accessible and reproducible, What was perhaps, was there a surprising challenge, or what was like an insight that you encountered while you did this transforming of an HPC-IO traces website into an REE?
Actually, when you are trying to transform something that was developed before into something that should be reusable, then you will actually see that a lot or many parts of what you have designed or what you have developed is not reproducible. You will see that, what I had before will not be usable in 1 year when the version of this dependency is increasing. So, and these are the things that usually people don't care or don't see. But when you consider, or when you want to have something that you are developing to be reusable in the future, or people can reproduce them, then it really makes it a lot harder to do, but it also will make it a lot useful for everyone, actually. I think
Mhm.
this was the most interesting challenge that we had.
Yeah, thank you for sharing that, Reza. And maybe to wrap this slowly up, because this is a short soiree.
There was one
I would,
question in the chat.
sorry?
There was one question in the chat. Maybe I can answer that
Ah,
briefly.
there was a question. Yeah, thank you for, because yeah.
Yeah.
Um,
Let me answer very quickly. So the question in the chat is how the community accept procedures of automatic theorem proving, because there is the impression that people in theoretical computer science assume that they do not generate data and that the publication of the proof on paper is sufficient. So I mean, I'm not that far into the automated theorem prover community, more in the interactive theorem community. But in the end, that's also a mix. So we do use automated theorem provers in interactive theorem proving extensively, just to generate proof. Because in the end, you will have to bridge the gap between your steps, and automated theorem provers are a great tool for doing so. Um, and then, of course, in when you want to publish about your work, if it's a formalization, then usually in your paper, you would write more broadly, what are the concepts, what are the problems, how did you have to formalize things in a specific way, so it works well with automation. But then these days we do have artifact evaluation for proof. So you will also likely submit a artifact that contains your proof, and then someone has to typically manually look at that and check if that is actually a proof for what you claim. And then so this is part of the proceedings for many conferences. And so automated proofs or fragments that come from automated proof procedures are certainly accepted there. And I don't think anyone in this community will accept a proof that is just on paper. So what you will find once you formalize proofs from paper to the computer is that, first of all, most proofs on paper contain errors. And secondly, most proofs that are on paper are proof sketch and not real proof. So they're more of a instruction of how can you get an actual proof from this proof sketch if you really want some. Yeah, so hopefully that answers your question.
yeah. If you have any back question, Christian, please. Okay, he says yes, thank you. With regard to our time schedule, I would like to close this beautiful presentation and conversation with like one last question, and that would be simply but importantly, what's the one thing that both of you wish more people would understand about your work? Why is it important?
So Reza, maybe you want to go first?
Sure. Um, uh, I think what is people are missing is that uh, any effort you put into to make what you are publishing to make it more reusable or more reproducible, the more people will actually try to use that, and the more impact it will have. So I don't consider the time that was spent in making this, let's say, website reproducible as wasted, or I would assume that more people would be interested to use that, and more people might be interested to continue working on that because it's now reproducible and people can actually use that.
Yeah, great. And so for me, it's I wish more people would understand how much of value it can add if you have mathematical documents that are interactive, that are not just PDFs, that actually contain the mathematics, but they also contain all the other aspects that you need. So the narration, the metadata, and all of that in one large interactive documents, and how valuable that is.
Yeah, thanks to both of you, Fabian and Reza, for your contributions. So I would really center on the word reproducibility and reusability to just center on the dissemination of the works, that more people will be able to access this and then to continue the work. And I think that makes a lot of sense. And yeah, thank you for putting the emphasis on that part of research data management infrastructures. And yeah, thank you for your work and your time for tonight.